Hello everyone, this clip will be on 3.3, which is about continuous random variable, and I will talk about the normal distribution only here. Okay, and let's see continuous random variables. Before this, in section 3.2, we talk about the discrete random variable where x, the values for x are discrete, like as a whole numbers 0, 1, 2, 3, 4, 5, something like that. But in this case, in 3.3, random variable x is being continuous, meaning the value of x cannot be like the whole number, like just a single number. The value of x could be interval or like disjoint union of disjoint intervals. This, so x is continuous if the value is either a single interval or a union of disjoint intervals. All right, and the probability, when we find a probability of this type of random variables, we need to measure over the intervals, okay, not just at the point. Before this, we find the continuous, the probability at like x equals 3 or p of x equals 5, something like that. So at a single point, but with this case in 3.3, we need to measure over the whole interval. So it will be something different, okay? Different formula for sure and different concept. For example, we could find probability of taking at least 32 minutes for the exam, right? Taking at least. So it is an interval, right? At least like more 32 minutes and so on, or taking between 31 and 33 minutes to complete the exam. We don't talk, when we talk about time, we usually we are not interested in like the exact time, exact minute, like exactly 32 minutes like that. So we are interested in like probability in an interval, okay? Now, instead of, for continuous random variables, instead of assigning probability to points, we actually find so-called probability density function. Okay, for discrete random variable, RV means random variable. What we find there is we find probability mass PMF, right? Mass function or PMF. But for continuous case, we the probability that we call it probability density function, okay? And we use fx instead of p. We use fx for probability density function or of random variable x, and the probability has to be greater than or equal to 0. So fx is greater than or equal to 0 for all x, okay? Must be positive or 0. Let's see the picture, okay? So the continuous probability density function, let me change the mark, okay? For the continuous case, now for the continuous case, the graph of distribution is continuous. It's like line. Before this, it's like histogram, right? It's like bars next to each other before this. But for continuous case, the distribution is continuous like a line. for example like this case. And when we find probability of x greater than a less than b, like as an interval between a and b, we are looking for the area under the graph. Okay, that means the shaded area, where x is from a to b, so the area from a to b, area under the curve here. So probability is the area under the curve. Okay, area of the shaded region. So, or probability is the area under the curve for a continuous case. Okay, so actually to find this kind of probability from a to b is actually the integral. Okay, it is calculus that you have not seen it before. The exact definition is just like this: the integration from a to b, integration of fx dx. Okay, this will give you the shaded area. And since we have not learned calculus yet, so don't worry about it. This is just the definition. We can find this kind of probability from, so we have probability table, just like binomial distribution. For this, we have probability table to help you find the value of p from the value p, which is a probability of x from a to b. Okay. Now for continuous random variable, we have these properties: p of x from a to b, okay, is the same thing as, when x greater than a less than b, is the same thing as p of x greater than or equals to a and less than or equal to c. That means with or without equal sign right here, with at include a or not, if it include a or don't include a, it still give you the same value of probability. Here you can take out the equal sign, because when we look at the area under the curve, it doesn't matter if we include that point a and b or not. We still it still give back the same value of the area, shaded area. So equal sign doesn't make any change for the continuous case. Doesn't make any change to the probability value for the continuous case. Okay, and also if you find if x is continuous, and if you write down p of x equals to a, find the probability at a single point. Of course, we cannot find it because at a single point, that means we are looking for the probability at like this. At a single point, there is no area under the curve at a single point, so the probability is 0. Okay, probability is the shaded area under the curve from a to b. So at the certain point, if you want to find probability, we have none, right? No area, so it is 0. And also, when we find the total area under the curve, the definition, if we integrate from negative infinity to infinity of the function f(x) dx, it is 1. It gives you the whole probability here. Okay, the area, the shaded area under the curve, all the way from left to right, we divide it as 1. Okay, the whole thing, the whole area is 1, like that. That means the total area is 1. Now go back to this picture about the discrete and continuous distribution. Right now we are on continuous case, and let's see the difference between probability distribution. For discrete distribution, it is countable, and our x, it's random. Like we have value, for example, 0, 1, 2, and so on. It's countable, like until 10. But for continuous distribution, we don't have like exact value, so x might be less than, say, 10, greater than 10, and less than 50, or equal, something like that. It's on an interval. So for the discrete distribution, x is countable, and continuous is uncountable. And also for discrete distribution, we have discrete points like this, and each point has its own probability. So p of x at a equals a is not 0, okay? But for continuous case that we talked about in the previous slide, previous page, p probability at exact point is 0, okay? So points have no probability. Now for discrete distribution, the probability we call the probability of this case the probability mass function, PMF, and we use p of x to represent that probability. Now for continuous distribution, we use f, okay, and call the probability density function. So we have PMF and we have PDF, okay? And of course, probability cannot be negative. It has to be 0, either 0 or positive. And for discrete distribution, if we sum the probability in the table, remember we have distribution table, if you sum of the probability, you get 1. But for continuous case, you need to integrate it. The total area under the curve, we talk about the area under the curve as a probability, and it will be 1 for the area, total area under the curve, like that. See this area, it's 1. Now to find the next expected value. Oops, it doesn't go. How come it doesn't go? What happened? Keep in ink. Okay. So for the expected value of the continuous random variable, if you want to find mu or e of x, you need to integrate it. We will not talk about it because we need integration, but you guys haven't learned the integration. But just for your knowledge, okay, so if you want to find expectation, you need to integrate from minus infinity to infinity of x f x. And to find the variance, you need to find e of x squared minus mu squared. That means you need to integrate x squared fx dx minus ex squared. That's it. Okay, now the famous guy for continuous random variable is normal distribution, because we use it a lot. It is really useful. The normal distribution, okay, is an important distribution. Okay, we use it a lot. Okay, let me change the marker. And it is a distribution of many population, for example, height, weight, test scores, or other well approximated by the normal distribution, okay? And well, with the survey, like when you do a survey with a big group of population, okay, usually the distribution is normal, okay. If your data are not skewed or anything, the distribution would have like bell-shaped curve. And normal distribution, well, can be closely approximated by normal curve, or we call it bell curve, okay. And or in some other books might talk about Gaussian curve. They are of the same thing, bell-shaped curve like that. Oh, not bell, like this, okay. And the density curve is symmetric about the mean. Oh, it's up here, okay, the graph is up here. It is the curve is bell-shaped and symmetric about the mean. So mean is in the middle, right? So left and right, they are symmetric, okay. Now, the total area under the curve is 1, of course, total probability. And the mean, median, and mode for normal distribution are exactly the same. So mean, median, mode are here in the middle. Mean, median, and mode. They are here in the middle, okay, for the normal distribution. Now, if X is normally distributed with parameter with mean mu, okay, when we talk about normal distribution, the parameters for normal distribution that we need are mean and standard deviation. So you need to know mean and you need to know standard deviation in order to work with normal distribution, okay. So we let mean to be mu and standard deviation we represent it by sigma, right? And if X is normally distributed, then we write down like this: X follows N. N stands for normal distribution with parameter mu and sigma. So mean and standard deviation, okay. Now let's look at the bell-shaped curve. Here, if X is normally distributed, we will have like a bell-shaped curve, okay, bell curve like this. And in the middle, it is mean, median, and mode. So mu is here in the middle, okay. Now, when you shift to the right a little bit, like when you add sigma to mu, so mu plus sigma is here, mu plus another 2 times sigma, 2 standard deviation. Here it's just mu plus 1 standard deviation. Depends on the value that you find. So if you add that to mu and mark it down here and mark here, and mu plus 2 sigma, mu plus 3 sigma. And to the left, if you subtract a sigma from mu, so mu minus sigma, mu minus 2 sigma, mu minus 3 sigma. Here, the area under the curve from 1 standard deviation right here, between 1 standard deviation left and right. So the area is actually 0.68, okay, or 68%. That means 68% of the data falls between 1 standard deviation. Now, if we move a little bit, stretch it to 2 standard deviation, the probability means the area under the curve up to here, to standard deviation here, the area is about 0.95, on about 95% of the data falls here within 2 standard deviation. And move a little bit off to 3 standard deviation from mean, then the data is about 99%, okay. Almost all of the data falls between within like 3 standard deviation. Okay, let's see more pictures. See, this is the summary, right? So 68% of the data falls into here, 95% are within 2 standard deviation, 99% falls within 3 standard deviation. And These are like normal distribution with different means to the left. Okay, different means mean your mu shift, right? But still have the same spreads, the same curve, similar curve but shift to the right. And with this, if the curve looks like this, mean the mean stays the same with these three set of data, but the standard deviation different. So the purple one has greater standard deviation, means the data is spreading out more than the blue curve, right? The blue curve means the data cluster together in the middle more than the purple one. Purple was spread out and flattened out. So same mean and different standard deviation. And here different mean, same standard deviation. All right, so let's see more. Now for the normal distribution, we have the spatial type, okay, which is so-called standard normal distribution. And we will be studying this because it is easier to manipulate the value than if we can find the value, if we can find the value easily and all that. So if we find the value with standard normal distribution, then we can transform or transfer the value to the non-standard normal distribution, right? And the standard normal distribution or Z distribution right here, it is normal distribution with a spatial value for mean and standard deviation. So if your mean is 0 and sigma is 1, then we call the distribution a standard normal distribution, okay? And we use Z instead of X. We use Z or Z for standard normal distribution. Standard normal random variable, right? We talk about English alphabet. So Z follows N and with mean 0 and standard deviation of 1 here. So if you see it value like this, the first parameter it's mu. So mu is 0 and right here sigma is 1. So all normal distributions are derived from standard normal distribution by shifting, scaling, or both. So we can work with standard one, and then we can scale back, okay, to the non-standard one. So Z follow N01, we can shift, scale, or both to the non-standard one, which is X follows N of parameter mu and sigma, which are not 0 and 1. Let me change, erase, oops. Okay, come back to standard normal distribution. We talk about the curve here. The mean value right here is in the middle. So again, it's the same thing, same area, but with the standard normal distribution, our mean value will be 0 in the middle. And so mu plus sigma will be 0 plus 1, and it is 1 here, and mu plus 2 sigma, mu plus 2 sigma is 0 plus 2 times 1, so it is 2 up here. So 1, 2, 3 actually, and to the left it's minus 1, minus 2, minus 3, just like that. Okay, and I need All right. Now, to find the probability when for a given z-score, now we can find the probability right here. So when we find probability, we talk about the area under the curve. So if we are looking for P of Z less than A, that means I have problem with my hold on. I need to erase this. Okay, I will not do the I should stop here. Hold on. And keep my ink. Alright, just do like this. I don't do the show presentation mode. So with this might be better. Now to find the probability of Z less than A, it is to find the probability of the blue area here. Okay, blue area here. P of Z less than A is the area under the curve to the left of A. So just like this curve here, A is here. To find the probability of Z less than A, it is this shaded area. Okay, like that. Now for continuous distribution, and also z-score is on the x-axis, and if you notice, if you observe here, mu is in the middle, and the positive z-score is to the right, and the negative z-score is to the left. Okay. So for continuous distribution, P of Z less than A is the same, is equal to P of Z less than or equals to A. So with or without equal sign, we have the same shaded area. Okay, doesn't matter you include the point A or not, it still gives you the same probability. Now we can use the table or statistical software, or Python. We'll do it in the lab. You can use Python to find the value of the shaded area. Okay, now for a positive z-score, okay, which means to the right of the mu. Okay, for the positive z-score, the probability of the normal random variable is less than or equals to the z-score. Okay, here. Marker. Highlighter might be better right here. For the negative z-score, usually the z-table or the normal random variable normal distribution table usually gives you the positive value, but if you want to find the probability when z-score is on the negative side, you can use the positive side and use like the symmetric property to find a probability of Z less than minus A. Let's see, we talk about this P, and when A is positive side, mu is here, right? Positive side, it's mean to the right of mu. So if your A is positive and you want to find probability of Z less than A, then it's just P less than the value is just like that. Now for the negative z-score, right here, for the negative z-score, minus A to the left of mu, like that. Okay, you can use the value from the positive side and then you subtract from 1, meaning that P of, see the shaded area here, it's the same thing as you take the whole thing and then you subtract P of z less than a. So minus a is here, a is here. See, you take 1 means here 1, subtract the probability of P of z less than a, then you get you actually get the tail area here, which is the same as the area of right here, P of z less than minus a. So because they are symmetric. All right. So again here, I write down nicely. So the whole area here, it's 1. The probability is 1 minus here. See, we give you the area, the shaded area when probability when z less than, z less than minus a. Okay, next. To find the probability when P of z greater than a, that means the shaded area is at the tail, at the right tail, like, and this one at the right tail. To find the probability of this case, the area under the curve would be 1, right? At the right tail, it's gonna be 1 minus P of c less than a, which means it looks like this. 1 is the whole thing minus the curve like this. See? So the whole thing minus P of z less than a will give you the tail area, right? Area at the tail. Now, the last one, if you want to find probability of the area from A to B, the area of under the curve from A to B, you can find it by taking probability of z less than b, so this shaded area first, and then subtract probability of c less than a. So you set that up and then you subtract a out, or this shaded area up to a, then you will get the probability of z from a to b. Okay, so you set this up. All right. Now, here is an example, the example of, do I save this? Okay, let's see. Example of the standard normal distribution table. So the table comes like this. Here is a z, the value of z. On the left column to the left is, right here, is the value up to 1 decimal place. For example, this is like 0.2 or 2.0 here, and you read the second place from here up top. So if your z score, z is 2.01 right here, then we have to read 2.01, so you have to read it right here. To the left, it takes the row, and up top is the column, and the second decimal place, second place, the first place is here. So for example, if your z is 2.21, then you read it here, 2.21, and the probability is 0.9865. So 2.21, you read 2.2, this row, and take this column 0.01, so the value is 2 z is 2.21, like that. Take this column, take this row, and read the probability from the table. Or for example, if you want to find p of z less than 1.12, and from the table 1.12 here, 1.1, right, and then read it here 2, the second place is 2, so 1.12 is here. It is 1. It's gonna be 0.8686 as a probability. So the value in the table is positive and greater than 5 because we are consider z on the positive side. So the area up to here, the area is 0.5, right, because the whole thing is 1. So if you see is false here more than mean, it means the area under the curve is going to be greater than 0.5, right? Or p when z is, okay, find the probability of z less than 2.38. 2.38 here, 2.3, oops, and 8 is here. So 2.3 is here and 0.08 is here. So 2.38, the probability is 0.9913. That means you are looking for the shaded area here. This is 2.38 and 1.12. That by this area. And next, usually they give you the positive value of z and find the probability. But in some book they might provide negative probability of when z is being negative. Okay, for example, this table. Okay, if we have this table, you're good too. And for the negative side, that means z is to the left of mu. Mu is mean, it's in the middle. So to the left of mu means your shaded area is going to be less than 0.5, less than a half, right? And to find the area of this, still read the same thing. For example, again, let me write down 0.5 is in the middle right here. It's 0.5. So mu, which is 0 in this case. So p of z less than a is gonna be less than or equals to 0.5 in this case. Okay, a is negative, like that. So if you want to find p of z less than minus, say minus 0.04, minus 0.04, go back, minus 0.04 is here, right? Minus 0.04, okay, like this. So it's gonna be 0.4841, which gives you this probability value. All right, now let's see example. Keep example like that. Here we are looking for A to E, right, to find probability. Okay, now we were working with standard normal distribution with Z. So Z or Z, let me change the ink, change the color of the ink. I don't know how to work with this PowerPoint. Okay, now our Z. Hold on. Go back. Marker. Now our Z follows normal distribution with mu 0, sigma is 1. So when P, we are looking for P of Z less than 1.52, we go back and look. Okay, look at the table. Maybe this one. So we look at the table here, 1.52. So Z less than 1.52. Where is it? 1.52 is here, right? So 1.5 and 2. Okay, so the probability is 0.9357. Here, 9357. Okay, so next part B, C less than minus 0.79. So minus 0.79 is negative side. So minus 0.7 is here. Okay, minus 0.79 right there. So the probability is going to be 0.2776, right? Read from the table. So 0.2776. Now part C, when P of Z greater than 2.51, that means we are looking for this area. But from the table has only area under the curve up to Z. This one, okay, right here. So we're looking for the area which is opposite from the table, right? Now to find this kind of area, we need to set up a little bit. So we need to find the area of the shaded area up to 2.51 first, right here, because we can find this from the table. So we need to look for this area first and then take it out from 1. That means when P is of Z greater than 2.51 means it is 1 minus P of, okay, talk about this. It's gonna be 1 minus P of Z less than 2.51 right here. So we are looking for the shaded area here. The probability of the area under the curve, it's gonna be 1 minus this guy, then gives you the area of the right tail, right? So from here, from the table, P of Z less than 2.51 is 0.9940. Okay, and subtract it out from 1, you get 0.0060. Okay, now part D, we are looking for P of Z between the two values. Okay, that means the curve looks like this. We are looking for the area of minus 2.55 here. The area between the C value between minus 2.55 and 0.09. So it's like that. Looking for the shaded area. So with this, you need to set up, remember, from here you need to set up P of Z less than 0.09 first and then subtract it. So you need to set up the value. means you need to take out right here. Okay, area this, you need to consider the area of P of Z less than 0.09 minus P of Z less than minus 2.55. Then you get the shaded area with the band 1, right, this guy. So set it up with begin with P of Z less than 0.09 and then take out this much. From the table, P of Z less than 0.09, let me see, P of Z less than 0.09, keep the ink, P of Z less than 0.09, go back here, it's 5359 and minus 2.55, minus 2.55, minus 2.5 is here, minus 2.55 is this guy, 0.0054. So take out these two value, go back right there. Now see 0.5359 and then 0.0054, you subtract it, you get the answer 0.5305. Now part E, looking for probability of Z greater than, oops, sorry, not on this side, on negative side is here, minus 1.21, and find this area. So it's gonna be more than 0.5, right, more than a half. From here, to find this, we need to do the opposite, because from the table is the area from the left until the value Z. So if you want to find the area to the right, then you need to set up, subtract from 1, right? So it's gonna be the whole thing, which is area is 1 minus this area up to 1.21, right? So from here, so from the table, Z less than minus 1.21 minus 1.2 is here, minus 1.2 and 1, so it's here, right? 0.1131. So 0.1131 is here, take out from 1, give you 0.8869. Okay, so this is to find the probability of the shaded area by using the table. So I'm gonna end it here now, and then we continue on the next clip.